Hey, welcome back. So today we're going to be talking about how to relate simple harmonic motion and rotation for a non-uniform pendulum for AP Physics C students. So this is based on the 2009 mechanics exam, and I know there's a lot of text on the screen. We're just going to take it bit by bit. I do want you to glance at the diagram here. So if you imagine you have a non-uniform bar that's suspended from a pivot point and it's disturbed from equilibrium like we have right here, then what happens is it will swing back and forth. And one of the things we're going to need to do is eventually find the period of this mass. So we're going to have to use ideas of rotation as well as ideas of oscillations to be able to solve this problem. So you're given a long, thin rectangular bar of known mass m, we know the mass, and the length L with a pivot that's up here attached to one end. The bar has a non-uniform mass density. I've tried to draw the image here in such a way that you get the idea that it's more dense towards the bottom. This X is going to be where the center of mass is. Notice it's not in the middle, it's some distance below the middle. So let's continue. The bar has a non-uniform mass density and the center of the mass is located at a known distance x from the end with the pivot. You are to determine the rotational inertia I sub b of the bar about the pivot by suspending the bar from the pivot as shown and allowing it to swing. Express all algebraic answers in terms of our moment of inertia, the given quantities, and fundamental constants. Alright, so the very first thing we're asked to do here, this is like the overall information for the problem that we're given. Down below here is the first instruction that we're given. It says, by applying the appropriate equation of motion to the bar, write the differential equation for the angle theta the bar makes with the vertical. So at first glance, if you see the term differential equation, some people slightly freak out, I think. Don't worry about it too much. It just means it's an equation with some variable and its derivative in the same equation. But let's go ahead and think about what we have already. So if we have this bar and it's off to the side, notice our force due to gravity is going to be applied at the center of mass, which is about right here. It's going to go straight down, and really the tangential component of that force, of that gravitational force, it's going to be the thing that provides the restoring force for this system. So we can go ahead and use that and think to ourselves, well, how could we start a problem like this? Now we're dealing with torque as we're dealing with rotation. So let's go ahead and use what I call the sum of the torque strategy, which is a variation of the sum of the forces strategy. All you do is you just say the sum of the torques and you add up all the torques that are operating on this. I could also have drawn the tension here. I think I did on the last slide, but we're going to ignore that for now because that provides no torque anyway. But we've got the torque, the tangential form of the torque, and that's it. That's what's providing the restoring force. And then the second line of the strategy is just to write I times alpha. And that's just like saying the sum of the forces is equal to the sum of the forces, and then say the sum of the forces is equal to mass times acceleration. This is the rotational version of Newton's second law. Once you do that, you can set these equal to each other, and you can say torque that's provided by the tangential component of the gravitational force is equal to moment of inertia times alpha. And we can say, well, what is that? Well, that force is going to be the force due to gravity times x, where x is the distance between the pivot and where the force is applied. Notice that if this x was longer and you had the same force, that would be a greater torque. So it does depend on the distance between the pivot point and where the force is applied. That's our x value, and that's why it's here. So then we define more carefully what we mean by FG tangential, and that's what we have right here. And our next step may throw people off slightly, so I do want to be careful about this. If we take the second derivative of angular position with respect to time, that is equivalent to angular acceleration. And I will talk more about that in just a minute, but before we move on, I do want to point out you do get a point just for doing this right here, for showing the sum of the torques, what they're equal to. You get a point for showing that this is a negative force. I do need to mention that this needs to be negative, and it's negative here as well, because that restoring force is going to be the opposite direction of displacement from equilibrium, which is exactly the same reason why Hooke's law has a negative sign in there. So that's one point, and then the other point is just the magnitude of this value is going to get you a point. So notice that it looks like an intimidating problem maybe at first. You're still getting points just for doing some basic foundational level work here. And you would also get a point for this, and I do need to go back and talk about what's happening here. I've created a graphic on the next slide to help us to visualize what I'm going to be talking about. As you go from this step to this step over here, keep in mind we've got our translational or our linear units. These are the rotational versions of them, If you take the derivative of position with respect to time, you've got your velocity, instantaneous velocity. You take the derivative of velocity with respect to time, you've got your instantaneous acceleration. And if you take the second derivative of position with respect to time, that will also give you acceleration. In a similar way, you have your rotational units over here, and these statements are true as well. So if you need to take a moment to pause and think about that for a moment, please do. Otherwise, it's expected that you understand this material that's on this slide and how to use that effectively. And that's why we were able to write this instead of alpha.
Let's look at the second part of the problem here by applying the small angle approximation to our differential equation. Calculate the period of the bar's motion.
So let's talk about the small angle approximation. We left off with this. This is our differential equation right here. One thing we can do is apply the small angle approximation. What is that? Well, that is the idea that for small angles, say under 15 degrees for sure, the sine of an angle in radians is approximately equal to that angle. So what you can do is instead of writing sine of theta, you can jump ahead and just write theta. Now, I'm going to come back to this and prove this to you in a moment, but this is what we mean by the small angle approximation. You can effectively get rid of the sine of theta, assuming you're working in radians. Then we could continue. We're going to isolate this term over here.
On the left-hand side,
one more thing we should do is draw out the theta, so then this becomes like a coefficient. We've got theta over here. Why focus on theta? Well, we've got this in terms of theta over here, and this in terms of theta. This is where you see it's a differential equation, and we can go ahead and take this and write it as alpha again, and the reason we want to do that is going to become clear in a moment. So now we've got alpha one more time after we wrote it as a differential equation. What I do want to do is think about what alpha is equal to in terms of other things that we know, and one of the most useful things you can do is relate things to angular frequency, this omega term over here. So when in doubt, try to bring in angular frequency somehow into your problem because it relates to just about everything. And so now we can set these equations equal to each other. So we go ahead and do that. Notice the two negatives are going to cancel, and the theta over here and the theta over here will cancel as well. So we're left with this equation. Now I'm going to run out of room, so I'm just going to label that as equation 1, and I'm going to drag that to the next slide when I move on to the next slide. But first I do want to talk about, as we're here, what points would you get along the way if you were able to pull this off? Well, you would get 1 point for doing the small angle approximation right here. So this is effectively something you should know. It's important, and it's used even in derivations like we have right here. And what else can we do? Well, if we can relate what we're working with to
omega,
we get 1 point as well. So that is what I was saying earlier. If you can relate anything to omega, please do so. So as I promised, this equation is going to appear on the next screen. And so we start with this. So we continue with this. And we're going to say omega, we know, is equal to 2 pi over the period. That is on your equation sheet. So we can change that to the squared version of it, and then we can sub it in, because eventually we want to calculate the period, right? So we're trying to get period involved, and that's what we're doing here. We bring in the period that way. Now we can cross multiply to simplify things, and we start to do some algebra to solve for the period, and we end up with this. So notice this looks similar to the period of a pendulum. That should be reassuring if you're able to get down to something like this. And on this slide, what you get is 1 more point over here, and you get 1 point for the end. So if you're able to set up most of the problem, if you're not able to get all the way to the end of the problem, notice you can still get a lot of points. So that's what I want to say, is just hang in there, get as many points as you can, and you can still be successful on the test, even if you can't get to the very ends of a problem. Okay, next we're going to move to the second and third part. These are going to be a lot faster. It says describe the experimental procedure you would use to make the additional measurements needed to determine the rotational inertia sub b. Include how you would use your measurements to obtain I sub b and how you would minimize experimental
error. And so remember, you've got
a non-uniform bar that's suspended from a pivot, and it's got a oscillation to it. So pause for a moment if you choose and think about what you would do for this.
Alright, so if you take a look at how the points are distributed, you get 1 point for a valid approach, 2 points for how the variables will be measured or calculated, including equipment to be used. How these variables will be used to determine the moment of inertia is worth 1 point, and how to minimize error is also in there as well.
So if you take a look at this,
this is an example provided by the College Board, and this student wrote, displace the bar by a small angle and release it to oscillate.
To reduce errors, time 10 complete oscillations with the stopwatch. Calculate the average value of the time for 10 oscillations, and then divide by 10 to determine the period t. Calculate moment of inertia for b sub I from this using known values of m and x. So this would get all of the points for this description. Now for part C, it says, now suppose that you were not given the location in the center of the mass of the bar. Describe an experimental procedure that you can use to determine it, including the equipment that you would need. So if you want, pause right now and see if you can come up with that on your own. Okay, so hopefully you thought about that, how you would go about doing this. This is actually really important to think about. You would get 1 point for a valid procedure, 1 point for the equipment to be used. So an example would be to place the bar on top of a fulcrum, like on top of a prism, adjust the position of the bar until it's balanced horizontally. The point at which this occurs is the center of mass. Or another example is just to place the bar near the edge of a table or a desk, and then slowly push the bar so it hangs off the table until it's just ready to tip. That point is the center of mass. So it's important to think about these things ahead of time so you can quickly come up with experimental procedures that you could use for various things. So hopefully this has been helpful. If you have any comments down below, please let me know.
And I hope you all have a great day. Take care.